This is an online learning (LMS) project. The task course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Reference book, Communication Systems, Simon Haken, Michael Moher. Content: Linear Time Invariant, LTI, System. Impulse Response, IR. Transfer Function and Impulse Response, IR. Low Pass and Band Pass Transfer Function. Filtering Effects, Ideal Filter. Channel Distortion Example. Communication Link Analysis, Gain. Linear Time Invariant System, LTI, Linear System. Input-output relation obeys the superposition principle. The output has a linear dependence on the input. That is, f of a times x of t plus b times z of t is equal to f of a times x of t plus f of b times z of t. Time invariant system. If the input signal x of t produces an output y of t, then any time-shifted input, x of t plus capital T, results in a time-shifted output y of t plus capital T. Impulse response, h of t. Response of the system against unit impulse or direct delta input is h of t. Question: Linear time invariant system, LTI. You are given an LTI system F with an impulse response h of t. Evaluate the following expressions. Capital F of 0.3x t plus y t minus x t minus 1. Capital F of direct delta t. Solution: apply the superposition principle of linearity. Also, the output of a system for a direct delta input is its impulse response. Convolution. Convolution of two functions gives the area overlap between the two functions as a function of the amount that one of the original functions is translated. Continuous form is defined as f convolved with g equals integral tau goes from minus infinity to infinity f tau times g t minus tau. So, the new function, y t, is the area at the time instant t, under the multiplication of f tau and g minus tau, where tau goes from minus infinity to plus infinity. Following animation displays the idea visually. Convolution. Continued. Here is another visual demonstration of continuous convolution. Discrete convolution. Similar to the idea of continuous convolution, discrete convolution operates on discrete signals. It is calculated by the summation m from minus infinity to plus infinity f m times g n minus m. Following is an example of discrete convolution. Visually, it can be interpreted as reversing one vector and then sliding it along the other vector one term at a time, and whilst taking the sum of multiplication of countering terms. Few of the terms of resulting vector y n is given explicitly also. Discrete convolution. Continued. Here is another visual demonstration of discrete convolution. Impulse response, IR. Impulse response of the system against unit impulse or direct delta input is h of t. The output of the system, y of t, can be found by the integration from minus infinity to plus infinity x of tau times h of t minus tau integrated with respect to tau. This is the convolution of input signal with impulse response. Question: Impulse response, IR. Impulse response of the following system, h of t, is equal to direct delta t minus pi over 2. Find the output of the following operation, y of t, when the input is sin t. Solution: y of t equals convolution x of t with h of t. Transfer function, frequency response. Time domain analysis of higher order systems would be complicated. Instead, use frequency domain analysis. Transfer function capital H of f is the Fourier transform of the impulse response h of t. Capital H of f is equal to integral from minus infinity to plus infinity h of t times exponential of minus j2 pi f t, integrated with respect to t. Similarly, h of t is integral from minus infinity to plus infinity of capital H of f times exponential j2 pi f t, integrated with respect to f. So h of t and capital H of f form a Fourier transform pair. Capital H of f can be expressed as an amplitude and phase term. So, capital H of f is equal to magnitude of h of f times exponential j beta of f, where beta of f is denoted as phase or phase response. Y of t is equal to x of t convolved with h of t in time domain. Whereas in frequency domain y of f is equal to x of f multiplied by capital H of f, the output spectrum equals the input spectrum multiplied by the transfer function of the system. Question: transfer function, frequency response. Find the transfer function of the systems whose impulse responses are given below. h1 of t equals 1, h2 of t equals sinc of t, h3 of t equals rectangle of t. Solution: find the Fourier transforms of the impulse responses. Transfer function and IR. Consider the system illustrated here, where x is the input, h is the impulse response and y is the output. Energy spectral density of the output function y of f can be found by the integration from minus infinity to plus infinity squared absolute of h of f times squared absolute of x of f integrated with respect to f. Question: transfer function and IR. For the system below, find the asked parameters x of f, h of t, h of f, y of f. Solution: it is more convenient to find the h of f first than find the impulse response h of t by taking its inverse Fourier transform. Low pass versus band pass transfer function. For filtering of a low pass signal, like an audio signal, this kind of transfer function is used. For obvious reasons, it has a spectrum shape suited for passing low pass signals. For filtering of a band-pass signal, like the signal at a radio receiver, which is also a tuner, the spectrum shape of a typical transfer function is shown in here. As you can see, the passing band of the response is centered at center frequency, and the shape is adjusted so that the desired effect on the input signal can be achieved. For a certain baseband signal, a filter is defined as h low pass equals rectangle f over 10 MHz, shown below. This baseband signal is upconverted, RF modulated, by a carrier frequency of 5 GHz. At the corresponding receiver, what should be the bandpass filter h of f? Evaluate and draw it. Use only positive frequencies. Take all amplitudes as unity. Solution: h of f equals rectangle f minus 5 GHz over 10 MHz. When a baseband signal is directly upconverted, it is just shifted to the carrier frequency in the spectrum. So, the filter defined for the baseband, h low pass, is just shifted to 5 GHz in spectrum. This band-pass filter enables us to filter out any out-of-band unwanted signal component, and gives us the desired signal in the passband. Ideal filter, brick wall characteristic. Ideal filter response in frequency domain of a transfer function is shown in the figure. It has a perfect rectangular shape. This transfer function h of f can be written analytically as exponential minus j2 pi ft0, when f is between minus and positive b. It is 0 elsewhere. If we take the Fourier transform of that function, we get h of t equals integral from minus b to b exponential j2 pi f times t minus t0 integrated with respect to f. This integral yields the result 2b sinc of 2b t minus t0, which is also shown in this figure. As you can see, there is no limit on the duration of the function, so it is generated at minus infinity in time and goes to infinity in time, which is unrealizable. So, the ideal transfer function, shaped as a perfect rectangle, cannot be achieved practically. As a result, we can conclude that limited time and limited bandwidth cannot be achieved at the same time. Example: first-order system. Temporal. Now, let us examine a first-order RC low-pass filter system. A first-order RC low-pass filter is implemented as the circuit, a resistance, in parallel with a capacitor. The transfer function h of t is, therefore, found as 1 over RC times e to the power minus d over RC times u of t, where R and C are the ohmic and capacitive values of the resistance and the capacitor. U of t is the unit step function. Figures show rectangular pulse responses for 3 cases of different input pulse widths. Question: first-order system. Temporal. To the given first-order system described below, pulses with different lengths are applied. Draw the pulse response for each case. RC multiplication is fixed at 10. x1 equals rectangle t minus 5 over 10. x2 equals rectangle t minus 50 over 100. The shifting in time is made for the pulses to be defined for positive time only. Solution: pulse response is found by convolving the input x with the impulse response h. For different pulse lengths, the response changes. Question: first-order system. Temporal. Continued. Now, let's see how the convolution works in more detail. For convenience, all amplitudes are taken as unity. Convolution of x1 of t with h of t is the area under the multiplication of the two signals when x1 of t is sliding across the time axis. So, for example, in order to find y5, that is, the result of the convolution at t equals 5, h of tau is multiplied by time inverted and shifted x1 of tau. The area highlighted is equal to 4 unit square, so y5 is equal to 4 when the shifted version of x1 and h have no overlap. The result is 0. Communication link: attenuation/gain. Consider an LTI system with a power gain of G, or capital G, which is also equal to 1 over loss. Capital G, in other words power gain, is usually used by RF engineers. In this system, the output signal power is denoted as the input power times G. G is the gain of the system. Remember that G is also 1 over L, where L is loss. G1 in multiplication is given in linear scale, but it can also be written in decibels. If this is the case, you cannot multiply G to get the output power. Then you should use addition or subtraction to apply the gain correctly. Study dBW, dBm, dBm etc. from EA 200 to 310. Make the following conversions. 1 watt in dB watts, 3 dB watts in watts, 1 over 2 ratio in dB, 20 decibels in ratio Solution. Be very careful about the units, and keep in mind that dB is itself refers to a ratio, but written as dB watts or dBm, it refers to a power level. Loss, attenuation, and link budget. Transmission loss or attenuation is denoted by L equal to 1 over G, which is also input power divided by output power. The output power in transmission lines can be found by 10 to the minus alpha script L over 10 times Pin, or it can be written in decibels as P out dB is equal to Pin dB minus L dB, where script L is the path length and alpha is the attenuation coefficient. Question. Loss, attenuation, and link budget. Calculate the input power of the following system. Solution. Loss is a decrease in power and therefore has negative value expressed in dB. Similarly, gain is the increase in power and therefore expressed positive in dB. Wireless communication link. Now consider the wireless communication link depicted here. P out is equal to G2 times G4 over L1 times L3 times Pn, or in dB form, P out is G2 plus G4 minus L1 minus L3 plus Pn. The loss in the system can be calculated by the formula L is equal to 4 pi L over lambda square. It is also equal to 4 pi FL over C square, where L is the length between the communication nodes, lambda is the wavelength. L1 and L2 are functions of wavelength and distance. Find the free space, line of sight, loss of the signals with the below parameters. Case 1, F equals 2 GHz, distance L equals 10 meters. Case 2, F equals 10 GHz, distance L equals 1 kilometers. Solution. L1 equals 58 decibels. L2 equals 112 decibels.